I will talk about the LCLS-I experience and a little bit about LCLS-II plans. If you're not familiar, this is a bigger project. It's somehow connected to the existing accelerator and also building a new LINAC to drive it, a superconducting LINAC to drive it. So I will give you a brief intro into FEL physics, very brief. Talk a little bit about the LCLS-I performance, current performance. Show you some highlights, some R&D efforts towards improving it and bringing out features for the science, short pulses, etc. And I will talk a little bit about the LCLS-II design. It's evolving a little bit, so I won't spend a lot of time with that, just end with it. Okay. So I like to start with this slide on a lot of these talks because I think it motivates some of the unique features that an FEL can deliver. And the idea is that, so I got this slide from János Hajdú some years ago, in fact. It shows this Coulomb explosion of a lysozyme molecule over about a 50 femtosecond span, and what might happen to that molecule as it's being imaged with an intense X-ray beam just before it is destroyed. So this is to give you some suggestion that we should try to produce femtosecond scale pulses, perhaps below 50 femtoseconds, in order to resolve the dynamics of molecular and atomic dynamics before this image that you're trying to take gets blurred by this explosion. So there's a motivation to go to short pulse lengths, and of course also hard X-rays can provide 1 angstrom level spatial resolution. So we're looking at pushing spatial and temporal resolution with these kind of machines. And so I'd like to put in context what a femtosecond means. Probably most of you know, but if I look at the time it takes for light to pass from the Earth to the Moon, I think I stole the slides from Sasha some years ago. It's about 1 second scale. Femtosecond is 10 to the minus 15th seconds, so that's about it's a 0.3 micron passage time through something like a fraction of a sheet of paper. So it's a really phenomenally short distance. And in fact, in Niels Bohr's 1913 model of the hydrogen atom, it takes about 0.15 or 150 attoseconds for an electron to orbit the proton. So these are phenomenal scales and the kind of levels we strive for with the design. What about the spatial resolution? So we're shooting for angstrom level wavelengths. So we do that with the Doppler shifted radiation. So imagine there's a stationary antenna, and the radio waves are produced by electrons running up and down the antenna wire. But if I put this thing on a rocket and I hit light speeds, you get a large Doppler shift, like 1 over gamma squared here, and you can push angstrom levels now. And now instead of oscillating on an antenna, the electron motion is now generated by a Wiggler magnet, like is done in the APS in many cases. So we get a huge boost from a high energy. So we like to have a high energy machine to produce these angstrom level wavelengths for these FELs. So this is a slide. I'll try to say something about the physics of FELs. I'll describe the resonant interaction of the electromagnetic field with the electrons. And the idea is that the electrons, of course, wiggle through the undulator, but I'll show you in more detail. I'm going to try to show you that the electrons slip behind the EM wave by 1 radiation wavelength per undulator period, or lambda u. So here's the undulator period. It's typically a few centimeters. And the electrons will run through this undulator, oscillating the whole way because these dipole fields are flipping sign. And if I look at now, of course, I'm producing light in spontaneous sense at startup here as the electrons wiggle through. If I pick the right frequency of light and the right phase to show you what might happen, I can accelerate the electrons at this particular phase. And if I pick the right frequency where I go a half of a wavelength later, I will accelerate that same portion again because the velocity has flipped and the electric field has flipped and I'm still accelerating. If I do that again every half period, I'm always accelerating at that 0 crossing point. And in the end, you hopefully will see that there's a resonant interaction going on for that one particular frequency. It's a narrowband amplifier, this FEL. And the radiation wavelength depends on the undulator wavelength. And here's the Doppler shift gamma squared, 1 over gamma squared. And then there's terms for the electron velocity difference between light and also for the path length difference for this oscillation. So K is the strength of the undulator or the magnetic field. So due to this sustained interaction between the electrons and the photons, Some electrons will lose energy depending on their phase here, and some will gain energy, producing an energy modulation on the electron bunch at the radiation wavelength. So this is the 1 angstrom scale. Now, some of the electrons will lose energy and slow down, and some will gain energy and catch up, causing a density modulation at the same microbunching level. So if I just recopy this and you imagine a shearing effect where the high energies are a little faster and the low energies are slower, then if I project this curve down onto the time axis, I would see high density spikes at 1 angstrom levels spacing. So this microbunched beam begins to radiate coherently at the radiation wavelength at this 1 angstrom level, which enhances the process, and therefore we get into an exponential power growth of the radiation power. So that's my fast FEL physics. If we look at other existing sources, and I plot peak brightness in the standard units against pulse duration in picoseconds on the log scale here, you see second and third generation sources where they lie. So storage ring-based sources like the APS here can get to brightness levels of 10 to the 23, perhaps a bit higher with the upgrade. But X-ray FELs are talking about quite a shift in 10 orders of magnitude shift in peak brightness. So along with that peak brightness increase, we also can get coherent X-rays, femtosecond pulses, and angstrom wavelengths. So they're quite revolutionary in concept. So you might ask, why do we use a linear accelerator instead of a storage ring? So I tried to explain. Imagine the storage ring. It has an emittance in the transverse dimension that depends on the energy squared, gamma squared. So if we want to go to higher energies, which I tried to argue earlier, to go to 1 angstrom levels, that means the emittance is going to go up, and that'll kill this microbunching effect that I explained earlier. It'll wash out the microbunching. So we also would like to have a good longitudinal emittance coming into this FEL, and the storage ring longitudinal emittance is much too large. The bunch length typically a few millimeters, the energy spread typically an MEV level, so the longitudinal normalized emittance is something like 10,000 microns. That may not be a familiar number, but I'll compare it to what you can get with an RF photocathode gun. Much smaller longitudinal emittance at about 4 microns, much less energy spread. These have been developed fairly well now and work quite well. And of course, to accelerate that generated electron beam in a LINAC, where the transverse emittance scales with 1 over gamma rather than this gamma squared of a storage ring. So it's very, very favorable scaling. But one compromise we take in doing that is we go to a lower repetition rate rather than the storage ring rate that can be megahertz levels. And I'll say more about how that motivates an LCLS-II as compared to the 120 hertz of LCLS-I. Okay, so I should talk about other planned and existing X-ray FELs. Every year or so I have to upgrade this slide. So of course there's Flash at DAISY, which has been operating for more than 10 years now at the sort of 4 to 45 nanometer levels. And in fact, I should mention just recently in the summer of 14, the Flash 2, this parallel extension that they built has seen first light too. So it's a very important step. And then in 2009, we got the LCLS-I to operate and saturate, and it approaches a tenth of a nanometer up to a few nanometers. Fermi in Trieste is a seeded FEL. It actually has 2 different FELs with different wavelength ranges and can cover about 4 to 80 nanometers. That's up and running since 2010, doing quite well. SACLA at Spring 8 Japan, similar wavelength range, and has been operating since 2011. The European XFEL at DAISY, of course, a very big machine with a superconducting LINAC, scheduled to have first light in approximately 2016. I believe this is probably slipped into 17 by now. The Swiss FEL at PSI near Zurich is also the same levels of 0.1 nanometer up to a few nanometers. This will be operating first light in late 2016 if things go well. That's under construction now and going a long way. The PAL, the Pohang Accelerator Laboratory in Korea, similar wavelength range. This was scheduled about the same time, late 2016. They're doing very well, lots of construction finishing up this year. And of course, the LCLS-II, which I'll say more about later, a little bit shorter wavelength extension, and 2019 first light date expected. But as I said, that's probably a bit optimistic. Okay, this is a picture of the SLAC site. Probably many of you have seen it. You see the campus of SLAC here is here. The old LINAC extends 2 kilometers long, and this portion of it was used for the collider, and that Sasha mentioned, the collider arcs are in this area. But we added a new injector at the 2 kilometer point back in 2006, and modified the existing LINAC for the last kilometer, which gives us about a 15 GeV beam. And then put a new transfer line to bring this electrons into this 130-meter undulator. There's a near experimental hall and a far experimental hall, and this is all up and operating now, but it gives you a sense of the layout. This is the undulator hall, looking, the beams coming at you. So all this stuff you see was, all the undulator stuff was designed and built at Argonne here, big player in this project. You start by seeing, here's one of the 3.4 meter magnetic sections. You can sort of see this, there's a shield around it. It's a mu metal shield to keep ambient fields away from the electron beam. It's very sensitive to small field errors. There's a support girder, and each girder can be slid on these motorized stages, so the undulator can be slid out in case we want to turn it off. It can be also slid over a continuum. The poles are canted slightly, so as you move at small angles, you can actually change the field and change the tuning of the undulator over small ranges. It's on cam-based 5 degree of freedom motion control, so that we can do beam-based alignment. Very, very tight tolerances on electron beam trajectory and alignment of all the components. Very tight, something like 10 micron scale over this 100 meter scale. There's hydrostatic leveling monitors, are half filled with water, and actually on each corner, and monitor ground motion, earthquakes, and level changes. Stretched wire over 140 meter, which also monitors best the horizontal component of any drift in the tunnel. Quadruple magnet and cavity BPM that was built here at Argonne as well. So all this stuff is up and working, and there are 33 of these undulator segments to make a 132 meter long FEL. And as you see on the right here, there's room for a second undulator. Everything was built large enough to do 2. And LCLS-II will fill this component and probably replace this undulator, and I'll say more about that. Okay, so this is the first measured FEL saturation at 1.5 angstroms. This was a very good day for us in April 2009. We measured the actual gain length at 3.3 meters, which is quite a nice number. In fact, the curve you see fit to the data is based on some parameters that some of it are inferred because they're difficult to measure. But the beam quality came out so good out of the gun and LINAC that we had built that the system saturated in 60-ish meters in a 112 meter magnetic length. So it came out very good. We had a very good result on right on the startup, and we were very happy with that. So as for routine operation, let's just say a little bit. Typically, we use the electron energy to change the photon energy wavelength of the photons from 3 to 15 GeV. That's actually gotten a little bit wider over the years because we found ways to do a little bit more. That means the photon energy, remember the undulator is tuned for 1 K value, except for this small variation scheme I talked about. So we have to change the electron energy to change the photon energy. So we can go from 0.3 keV up to about 11 keV just by tuning the electron energy. It can take half an hour to change the frequency if it's a significant change. The X-ray pulse length, we talked about 200 femtoseconds in the original design, but if you run soft X-rays, perhaps 1.7 or 2 keV level, we find you can actually vary the pulse length with a bunch of compression systems. So it can be almost anything over this range, depending on how hard the X-rays are. Maybe not worth getting into details, but if we push hard X-rays, this range will close up a bit. The bandwidth typically is about 0.1%, but since we've developed this self-seeding schemes, we can go as low as 0.005% or 5 × 10⁻⁵. And if we chirp the electron beam, the SASE beam will also be chirped, and therefore we can push up to close to 2% bandwidth. So it's quite a wide range of operation. The repetition rate has always been about 120 hertz, although we started up a little lower rate. And the machine is, so this gives you a picture of the estimated, the full width half-max pulse length in femtoseconds from 50 femtoseconds up to about 500 femtoseconds. And this is at 1.7 keV, and you can see just by playing with the compression and changing the pulse length of the electrons, you can still get anywhere above 2.5 millijoules of pulse energy with any of these pulse lengths. So it's quite adjustable. And there's also ways to get below 10 femtoseconds by lowering the charge to 10 or 20 picocoulombs, and I won't get into too much of that. But okay, so now I'll say more about what has happened since the commissioning. We've been taking people's ideas and trying to think of new ways to add features, and one of the latest was X-ray self-seeding with the hard X-rays. And the idea comes from Daisy, Geloni, and others. And it's a collaboration, actually, we set up between Argonne, TIS, NCM, that's a Russian institute near Moscow, and SLAC, of course. The idea is to put a magnetic chicane somewhere in the middle of the undulator, approximately the halfway point. I've drawn it way too big here. It's only 3.5 meters long. And then the electrons will bypass a diamond crystal that will be inserted into the photon beam. And this is a very high-quality diamond. It has a particular Bragg angle depending on the photon wavelength. And this diamond will generate a tail, a temporal tail, that's a monochromatic tail, and it can then interact with the electrons as they come back into the same second piece of undulator, so that the monochromatic photons from that crystal will self-seed the electron bunch as it comes in. So the idea is to self-seed to make very narrow bandwidths, and I'll show you how it came out. This is a picture of the setup. This is supposed to be a picture of here. Unfortunately, I got the beam reversed in the two pictures, but just details. So you see the chicane magnets. They're kind of blue and white. The diamond is housed in this behind this 10-inch flange here. There's a Bragg diagnostic screen at the top, so you can see the Bragg reflected X-rays and see if it's working right. This was put together by Argonne too. It doesn't show the beam in that picture, but it eventually made it there. This is the 10-inch flange you see here. It has a nice motor control, all built by here at Argonne, and it has a little diamond crystal at the very tip, which you probably can't see if I blow it up a bit. There's a graphite holder, and the diamond is housed at the very end and can be controlled in pitch angle, yaw angle, X and Y position, and then you can to line it up with the photon beam, and the electron beam goes around that. And I think there's a picture here that shows, you probably can't see this, but there's the graphite stock. You're looking down the beam tube before it's installed. The diamond sticks out like a little flag, and then the two beams, one intercepts and one bypasses because of the chicane. So that's the idea. We put together this hardware, installed it in January of 2012, and here's some of the results. So this is a spectrometer, hard X-ray spectrometer at the end of the machine, and it shows a SASE spectrum. This is typical noisy SASE spectrum that comes out of an FEL. This is about 20 EV full width. Now the chicane is off here. If you now insert the diamond, this little graphic shows you the diamond going in some way. And now turn the chicane on. Of course, it doesn't happen this instantaneously, but we eventually, after a few days, got it tuned up. And the bandwidth is now, instead of 20 EV, it's a half an EV. So we get about a factor of 40 to 50 bandwidth reduction by doing this nice crystal insertion. And here's the profiles shown out. So you can run SASE with the diamond out or run seeded with the diamond in. And it's quite easy to switch between those. I should warn you, I'm showing you a very nice pulse. It's not typical. The shots vary quite a bit from shot to shot. It's because the old copper LINAC has been around since the 60s. Is not as stable in energy as you would need for this kind of monochromator. But we're working to improve that. So I'm just showing you a nice one. Okay, we've also looked at soft X-ray self-seeding. What I showed you before was hard X-ray self-seeding. The idea again, and it's actually an old one from 1997 from Daisy again, is to put a chicane in the undulator. Someday I'm going to open a business in chicanes. I think I'd make a lot of money, but so put one. Actually, this one is a little bit earlier in the undulator. The other one I showed you would be over here somewhere. And then you put a grating-based monochromator in for the photons. Once again, the electrons go around. And the photons will disperse on the grating, and there is an angle-controlled mirror here that and a slit, and you can choose which tuning by choosing the angle of this M1. And then the photons come back in line with the electrons, hopefully. But and here's a picture of it. I think this is going right to left again. Here's the can for the first M1 and grading, and this is the can for the M1, M3 and M2 mirrors. It's a little hard to tell. But this is a different chicane than I showed you before. The grading was built by PSI. In fact, this was a collaboration including PSI and Berkeley. And this is the inside of this 10-inch flange, which you see right here. Oh, sorry, this is M2 and M3, which is right here. So you see the two mirrors here, and they're controlled with motors, and they can be retracted, et cetera. And we also had to have overlap diagnostics. For the one I described earlier, the hard X-ray, the beam goes nicely through the X-ray, nicely through the crystal, and does not deflect transversely at all. Here, we get this large deflection of the photons, so we have to be very careful that we put them spatially back on top of the electrons, and that's a level of complication that turned out to be more difficult than we anticipated. We put in overlap screens so we can pop a screen in and look at the electrons and the photons and overlap them spatially, both in position and angle with two screens. And then the temporal adjustment is made by the chicane strength. You can advance or delay the electrons, so we have to spatial and temporal overlap. And this device should go from 300 to 1200 eV, so it's really soft X-ray self-seating. The other one I showed you, the hard X-ray, was this, I think it could go down to about 4 keV and up to about 12 keV, although 12 keV is a bit of a push for our machine. So this is the result from the soft X-ray self-seating. Here's the SASE profile in spectrum with a 10,000 shot average, and that's with a 50 femtosecond pulse. And here's the seated bandwidth after a lot of work getting the overlap correct. So it works quite well. This one has also got some stability issues, again, because of the electron energy is not completely stable. So the bandwidth is about 30 times narrower than SASE at this nearly 1 keV level, and the 10,000 shot average spectral brightness is about 5 times higher than SASE. We're working on improving it, but that's what the latest is. There's a publication coming out very soon in Nature Communications. And I should point out, Daniel Ratner is the young postdoc that led this effort. He's done a fantastic job, and I want to make sure he gets recognized. So I'll talk a little bit about transverse RF for time-resolved measurements. This is an old idea. It goes back to the 60s, but we revived it and maybe found new tricks. The idea is to install a transverse deflector, not an accelerator, but an actual transverse RF deflector. And the idea is to bring the electron bunch in. It sees this fast-varying field. The head of the bunch gets kicked up, the tail down. Put a screen in its way, and it'll show you the bunch length. So they're a very simple single shot, I think it says single shot, absolute bunch length measurement, because you can vary, I won't get into it. So we put one small one in the injector, and this is showing you some real measurements that were done. If you turn the RF deflector off and then turn it on, you see a huge streak. It's like a streak camera almost, but it's a much better resolution scale. You can see the time-resolved bunch. So maybe this is the head, and maybe this is the tail, and you're seeing the whole bunch laid out for you in its time coordinates. You can measure the beam quality in the slices, in the time slices, which is important for an FEL. So that was for the injector. That's about a 0.5 meter S-band device. We've recently installed 2 X-band cavities. You can sort of see them here. The beam is actually running, I think, right to left here. These are 2 2-meter sections, or maybe, they're 1 meter sections. And this is X-band, which is 11.4 gigahertz. So the higher the frequency, the better the temporal resolution available. These were installed after the undulator. That's important, so that we can see the FEL process, and I'll try to show you that. So the idea is, with the FEL off and the deflector installed, and there's a vertical bend. Remember, the deflector is horizontal, and the vertical bend is vertical, of course. If I turn on the FEL, what happens is some of the electrons lose energy because they lose it to photons, radiation. So you would see a streaked vertical beam just from the FEL process. And I show you that here. So this is the energy spread on that screen after the dump magnet from the FEL process. But notice the transverse RF is off. If I switch on the RF, suddenly I get the other dimension, this coordinate streaks. and I'm seeing the time dimension and the energy dimension. So this is longitudinal phase space, and this is measured, not simulated. Now, if I turn the FEL back on, what I see is what used to be a small energy spread now grows quite a bit because the FEL process is degrading the energy of many of the electrons, but depending on which electron and which characteristics it had. So you're seeing a direct FEL observation. And what we can do now is you can take the projection of this effect, take the average loss compared to the average before the loss, and calculate many things. You can estimate the X-ray pulse, which is, if I remember, the blue and the red are the X-ray pulse. This is femtoseconds, so you see about 100 femtosecond pulse. You see the shape of it. The two colors are because one is done using the energy loss of this profile, and the other is done using the energy spread. They should give you the same result, but we do it both ways. And the green one is since we have temporal resolution, and we also know that bunch charge, we can actually reconstruct the electron profile. And it's, notice, I should hit this button, it tells you that everything here is absolute scale. So I don't have, if I calibrate this device with beam, so it's foolproof, I think, these profiles come out with units of gigawatts, femtoseconds, and kiloamps. So it's not a relative monitor, it's really absolute, and that's a wonderful thing to have. So this is in operation and can actually, since the FEL X-rays continue on straight here, they don't care about the vertical band magnet, of course. We can fire this anytime and all the time because these electrons are headed to the dump anyway for being discarded. So this is a fantastic diagnostic with really nice resolution, and the users can actually look at the profile of the beam nearly shot to shot if it's running. Oh, this reminds me I should be halfway done. I think I am. So I'll talk a little bit about lasing control with a slotted foil. This is an old idea we put together back in 2004. The idea is when there's a bunch compressor made of dipoles, which the LCLS machine, this is supposed to be the LCLS accelerator, there's a bunch compressor to compress the bunch. And if we put a foil in there with a slot, what we can do is spoil some of the electrons, most of the electrons, but the electrons that go through the slot will not be spoiled. And that's important because there's a time, you see it sort of drawn here, a time and X correlation in the beam at this point. It goes away before and after, but in the middle of the chicane, it's there and you can use it. So you can actually spoil the head of the beam and the tail of the beam and leave a little slot, a little portion unspoiled. What will happen is the FEL will only respond to the electrons that pass through the slot, and the rest will be suppressed, and you can make a very short pulse that way. Of course, you lose photons, but you can control the pulse length. So it's the foil is inserted into the BC2, that's the second chicane. The X position is correlated with the energy time, as shown here, which spoils all but a narrow slot. And this yields an ultra-short single or double FEL pulses, and I'll show you that. So the foils are there. We made up several foils, one with a single slot that's adjustable, so if you move the foil up and down, you can change the pulse length. So you're shaping a femtosecond X-ray pulse by moving a motor up and down in the chicane. So it's a nice scheme. And in addition, we built double slots, and I'll show you what those do right here. So the idea is you put the beam across one of these double slotted foils, sort of the dimensions indicated, and if I play with a motor on top to drive it in and out, I should see this on the FEL pulses, and it seems to work out. I think the next slide will show. This is the foil we built. It's a kind of a bad picture, not that pretty of a foil either, but the idea is, so you're looking at this single slot area with a taper on it. There are other double slots, which you probably can't quite see. And the idea there is, so if I put the foil into the beam at the BC2 location, and I leave the FEL off, and I note this picture, this is, remember, femtoseconds as streaked by this X-band transverse deflector. The vertical coordinate is energy because we're bending downward. So this is the longitudinal phase space of the electrons without the FEL. And of course the foil is in upstream. If I turn the FEL on, suddenly I see some of the electrons lose energy, but only the ones that went through the slot of the foil. And now I've got an X-ray pulse with 3 gigawatts of peak power with only 5.5 femtoseconds full width, just by putting that foil in. The transverse deflector is just a diagnostic. And this is work done by Christoph Behrens and Yuntao Ding and Tim Maxwell and others. I can also put in a double slot foil, FEL off again just to get the baseline. Turn the FEL on and you see two prongs come. Remember, it's energy loss to the FEL process. And now I have two 5-ish micron pulses with 30 femtosecond separation, and I can change the separation simply by moving the motor of this foil up and down. So I didn't show you that, unfortunately, but it's a nice method that's quite simple and people have relied on it. So another thing you can do with this foil and with the hard X-ray chicane, the hard X-ray self-seating chicane I referred to earlier, take the foil with this single slot scheme, bring in a bunch to the BC2 chicane. Remember, the foil is in the middle. The chicane will compress the electron bunch. I've tried to show that with a shorter bunch. And now the first half of the undulator has a particular K value, which we've tuned in by this adjustment effect I tried to talk about earlier. And now, of course, we will produce an X-ray beam. If it's soft enough X-rays, this can't be endlessly hard X-rays. That follows the electron beam after this half undulator. Now, if we go past this hard X-ray self-seating chicane with the diamond removed, it gets complicated. The electrons will travel a bit longer path, about 20 femtoseconds in this case, but adjustable with a chicane. And now we take it through this last half of the undulator, which has its own K2 value. It'll be within 1% of the other one because that's the limit of the tuning range. And now I have two different color pulses that are about 20 femtoseconds separated. And this was done, that's the limitation. This was done, this is an actual spectrometer measurement in the soft X-ray hutch with about a 20 EV separation at 1.5 keV. This is just this is probably not worth going into. It's restacking the line out profiles so that you see you get away from the energy jitter effect of the machine. Too hard to explain quickly. And this is Gentao Ding again with Alberto Lutman and Ryan Coffey did this and published it in PRL in 13. Okay, another scheme that's been put together by Ago Marinelli at SLAC is also a variable double pulse scheme, but in this case he double pulses the drive laser for the cathode. And now you see two beams going down the LINAC very close in time, about 5-ish picoseconds apart, adjustable of course. Normally, so that's within one of the RF buckets, whereas other schemes talk about putting beams in different buckets. But these are very close together. You accelerate these two pulses, the linear chirp can be removed by the wake field of the accelerator. That's a standard treatment. And here's a picture of the two pulses as they come off. This is the transverse cavity again, so I'm showing you femtoseconds and power in gigawatts of the X-ray beam. And this is tunable from 10 to about 100 femtoseconds in the separation, depending on how you set up the initial laser. Here's the spectrum for that same scheme at about 8.4 keV. You see two semi-wideband pulses because this is sassy. Ago tells me he can actually use the seated scheme on top of this double pulse scheme, and he can make two seated pulses and has done so. Again, the same 8.4 keV, much narrower bandwidth because this is seated, self-seated. And we'll skip this and move on. There's Ago now, just to see the guy doing all the work. We've also started a program we call the Delta Undulator. This is a scheme devised by Sasha Temnik at Cornell. The idea is to have build a special undulator with 4 sliding permanent magnet rows. The whole thing is about 3.2 meters long. And with these adjustable rows of permanent magnets, you can have field control from 0 up to maximum. You can produce, depending on how you move the rows of magnets, you can generate planar, elliptical, or circular polarization of the FEL light. And this 3-meter section was installed in October of 14. You see the argon undulators up here, the cylindrical shape. And then the very last one we recently swapped out with this new Delta scheme. We used a daisy polarimeter, which they brought over here and set up for us. I won't go into the details because I don't understand them that well. But with linearly polarized light or circularly polarized light, you can use the divergence of the beam to figure out which you have. And some of the early measurements suggest we have circular polarization using this delta at some low level. I won't say much about it because it's only a couple weeks old, and I don't really know that much about it yet. But it's a nice effort put together by Heinz-Dieter Nguyen at SLAC, who spent 3 years coming up with this guiding this effort and coordinating all the work that has to go into building a new device and installing it and commissioning it. Okay, so what are the new directions for the next facility? I'll say a few of them. So we like to build seeded FELs for narrow bandwidth and full coherence. There's a lot of interest in pushing for terawatt levels into peak power. That can be done using seeded FELs with a strong undulator field taper. We'd like to push toward higher repetition rates and perhaps continuous wave operations, so the bunches come rather than in bursts, it would come at a predictable and continuous rate. We'd like to push for sub-femtosecond pulses, perhaps below into the attosecond range. The facility should probably have multiple FELs with independently tunable wavelengths. Lots of demands, right? Pulse length and bandwidth control at the transform limit. Two-color pulses with variable relative timing and color. We've done some of this, but of course there's a long way to go to make it flexible enough. And of course an expanded facility that can be used well into the future. And of course this for a while was called the Next Generation Light Source and was centered at Berkeley. It's recently moved over to SLAC again and it's called the LCLS-II. I did the same moving from Berkeley. Okay, some of the baseline features. We were asked by the BSAC, the Basic Energy Sciences Advisory Committee, sub-panel meeting in July of 2013 to devise a machine that follows these key issues. I'm not putting everything down, but it should have a high repetition rate, which we answer by building a continuous wave superconducting megahertz scale LINAC. I'll show you more about that. A broad energy range, we meet that by building a superconducting LINAC and using the existing copper LINAC that's been used for years to drive LCLS-I, and with variable gap undulators. We should have a transform limited beam capability. We would do that with self-seeding, which has been demonstrated, but needs some stability improvements. We want to make an ultra-bright beam, and that's done by very high electron energy with the copper LINAC and high K undulators in the hall. We like to have multiple undulator sources, and we've met that by proposing to build two different undulators that target soft X-rays and hard X-rays separately. And as I said, this LCLS-II first light is planned for the end of 19, and I keep reminding myself and others that that's probably optimistic, but it's the official goal right now. So here's a very cartoon-like sketch of what this machine should look like. And we build a superconducting continuous wave LINAC. This would be I think it says a 4 GeV LINAC at up to 1 megahertz repetition rate. So that's a big undertaking all by itself. And remember, to put this, it's about 1 kilometer of LINAC. To put that in, we have to remove all the old copper structures and gut the tunnel. And I'll show you briefly about that. We take that beam into either a soft X-ray undulator, which would span 0.2 to 1.3 keV, using this 4 GeV beam, a very high repetition rate. Or, and this could be a fast kicker, could be every microsecond we switch from one to the other. This could be the hard X-ray FEL, which is a bit longer. And then you'd have 1 to 5 keV possible in that. And one more operating mode, use the existing copper LINAC to go from up to 15 GeV, just like we've been doing for the last 5 years. And this would extend the range in this hard X-ray undulator from 1 to 25 keV, so that's about 0.5 angstrom. To see the operating modes, the copper LINAC with the 3 to 15 GeV at 120 hertz could run SASE from this 1 keV level all the way up to 25. We could do self-seeding of that beam from about 4 keV up to about 12. I'm hearing from Yuri Shvidko that we might be able to go even lower. The superconducting LINAC at 4 GeV, that's the high rate LINAC, would go from about 0.2 keV up to about 5 keV, depending on which undulator you use. And we could do self-seeding in the low range like we have done now of just under 1 keV. So that's a quick introduction to what LCLS-II looks like. Keep in mind, LCLS-I is still here, although its undulator might be replaced by an adjustable gap version. I think I'm just going to skip this. It just gives you a feeling for, here's the superconducting LINAC way back here. This is about you see the scale in meters down below. So this is about almost 4 kilometers of layout. The first kilometer has the superconducting LINAC. Then we go around this other middle kilometer of LINAC, which may be used for a different set of experiments. and go around the existing LCLS-I and feed these two undulators through this long bypass line. I think I'll show you a picture of that in a minute. I won't go through all the details of what we have to change. I want to mention that we have collaborators on this project: Fermilab, Jefferson Lab, Berkeley, Argonne, of course, and Cornell. Much of this, I won't go through the details of this, but much of this work is focused on the superconducting cryomodules and cavities for the LINAC, which is a big effort. I think I will do this very quickly too. Just make the point that we need a special gun, because a high-rate gun needs a lot of cooling, needs a lot of vacuum pumping, and Berkeley has developed something they call the APEX gun. It's been operating for about 2 years now. It's supposed to feed a 750 keV beam of high brightness quality into one cryomodule. This is the standard Tesla technology up with 100 MeV acceleration, and then the LINAC starts here. A lot of work has been done to progress this. These are simulations showing the beam quality as possible, the peak current, et cetera. And there's, like I said, there's lots of pumping. So this is our baseline choice for the gun, but Cornell also has a competitor that we're considering, more of a DC gun, that has produced very nice results. Remember, the key here is the high rate. So it's a different kind of gun than the one that exists in LCLS-I, very different kind of gun. But it needs to produce similar quality. Maybe this is detailed, but this shows the bunch compressor layouts. There's always these chicanes in every LINAC for an FEL because the bunch is compressed in length in stages so that you don't compress too fast, which would cause the beam to blow up due to space charge forces, but you do it after the energy is high enough to reduce those space charge forces. And from this you can come up with the accelerating gradients for each cryomodule or section of LINAC. It's right about 16 megavolt per meter, and that's our goal for now. Each of these cavities in here would have their own solid-state amplifiers. And this is some preliminary tracking of the beam through all these effects, wake field effects, et cetera. And I mentioned this long bypass line, which is trying to show here. It's about 2.5 kilometers long, and it's a 1-inch pipe, and it just runs along the ceiling of the LINAC tunnel. And because the beam runs in this thing, it's a very short pulse and interacts with the chamber of the beam. And there's a resistive wall wake field, which nicely cancels the linear chirp in the beam that the RF leaves. So we count on the effect of a resistive wall wake to flatten that beam profile. It sounds a little iffy, but I think it makes sense. These are the RF parameters. This is a very a key part of this machine to get this using the existing Tesla technology that Daisy has developed, but to get a bit higher in the Q value. This is sort of like the quality factor of the cavities. We're shooting for 2.7 times 10 to the 10th. And no one has done that level before. It's always been in the 1 to 1.5, 10 to 1.5, 10 to the 10th. But there's been an effort, and I think I show it in the next slide. Yeah, there's been an effort to do nitrogen doping. I think the scheme that was proposed and actually developed at Fermilab. There's been a program to demonstrate that this nitrogen doping of the cavities during their heat processing can work. And these are different cavities, 9-cell cavities in vertical test at Fermilab, JLab, and Cornell. And we're required to get to 2.7 times 10 to the 10th in order that the cryogenics plant is a reasonable scale. If this number goes down, we need more cryogenics power, and that costs money. And you can see the required level versus the actual demonstrator level is optimistic right now. We're above the requirements on all these cavities. This is a huge, Mark Ross gave this slide to me. He calls it a game changer, and this could also be used for linear collider work, which would benefit greatly from the high Q. And in addition, the gradients, we need 16 megavolt per meter. The average that's coming out of these 3 labs, again, doing the same techniques so that industry can take over, is above that at about 19 megavolt per meter. So this is a big deal. To develop this acceleration gradient and Q0 in future LINACs will go a long way, I think. This is I think I'm coming to a close. This is the SLAC tunnel as it exists. Maybe some of you have seen it. The S-band accelerating structures are here, copper structures. You're seeing mostly water cooling lines, input transmission lines here. There's a strong back and alignment vessel. I won't get into the details. But you can see it's not particularly roomy. The idea, though, is we need to remove 1 kilometer of this stuff in the first kilometer of the LINAC in order to make room for the superconducting LINAC. We need to replace, replace that kilometer with the superconducting LINAC, and we're going to use the existing PEP2 bypass line. And if you see, it's up here. It's a little hard to make out, so you can sort of see it along here. That will transport these beautiful electron bunch that we make back 2 kilometers earlier and take it all the way to the undulators. And there's some impedance issues associated with that line. But they're, in fact, in some cases beneficial, believe it or not. So now how do we fit the cryomodule into the tunnel? This is, for example, the cross-section of one installed cryomodule. The SLAC LINAC tunnel is only 11 feet wide by 10 feet high. But we also have to make room for transported cryomodules so we can replace them, and enough room for people to escape in emergency, et cetera. So it's quite a tight fit. Remember, we're not building a greenfield machine. We're building based on an existing facility, and there are real limitations. Now I'm just going to mention about, we're also looking with Argonne here and with Berkeley at superconducting undulators. Argonne has done a lot of work, as has Berkeley, to develop this technology. In fact, the APS has a 0.5 meter SCU0 installed for the last 2 years, as most of you probably know. The present plan for LCLS-II is to use permanent magnet adjustable gap undulators. But if you use those and you calculate the average X-ray power from this FEL at this high rate versus the upper limit photon energy range that we'd like to meet. Remember, BSAC told us to hit at least 5 keV. In fact, we're just a bit short of it if you put in reasonable numbers. So the hard X-ray FEL cuts out just about 5 keV because beam quality issues and the permanent magnet choice of the undulators. If you look at different undulator technologies instead of the permanent magnet undulators, but perhaps niobium titanium, which Argonne builds, or the niobium 310, which Berkeley is developing, we can do a lot better in field. So there's some interest in changing this idea, although it takes some politics as well and money, to these technologies. Presently, the LCLS-II permanent magnet solution lies right here with a 26 millimeter period and a 1 Tesla field. If we instead move over in this range with shorter period, maybe 18 millimeters, depending on which of these two technologies works best, and we've got an R&D program in place to decide between these two, then we could get nearly 2 Tesla fields. And field is everything here because it couples the electron power into the photons. And the better the field and a good quality undulator, the better the performance. And if I now update this picture with those two technologies, you see we go from 5 keV or a bit less out to 6.5, perhaps closer to 7.5, depending on the two schemes. This niobium 310 is nice, it looks very promising, but it's the riskier of the two. So we'll have to decide performance versus risk soon. Probably next summer. This is a picture of the work going on here at Argonne. There's similar work at LBL. This is one of the cores for the SC1 that's going into the APS. And of course, we're going to build more of these, I hope, for LCLS. That'll be 1.5 meters long, so very similar length. They're learning a lot down at the building 314 right now, and hopefully this technology will develop. Here's a nice picture from Joel showing the conceptual layout, how it might look in the SLAC undulator tunnel with all the cryo distribution pipes enclosed in these cryomodules. They'd be about 5 meters long per cryomodule. We've got a conceptual design laid out anyway. And I think this is the last slide. We also have future facility expansion ideas. So SLAC has extensive infrastructure, and you can imagine new tunnels are possible on each side of the existing LCLS. So this green thing is the existing LCLS. There's only one undulator in it right now, but of course we could stick another one in. That was always the hope. But we could dig new tunnels on each side and put new experimental areas. In fact, this side has already been planned out because before we changed last year from LCLS-II phase 1, which they call it, which was the normal conducting LINAC, before that, this tunnel was all scoped out and ready to dig until our plans got changed in favor of this new superconducting machine. But that's still a viable option. The other side is reasonable too, of course, it's money. And then there are these fixed end stations. These are the old fixed target end stations from the HEP days in 1960s and 1970s. They still exist. There's room for undulators. Not quite as much as new tunnels, but we could populate them, for example, with the superconducting undulators, which are more compact and efficient, or maybe FEL oscillators like Quan Jay would like to see. So there's lots of room to expand, and we hope we'll do so. And I think I'll stop there. So thanks. Questions? I don't blame you.
So, Paul, how they are planning to separate the linear polarization from the main undulators and circular, whatever polarization will come out of delta?
The delta?
Yeah.
How do they say it again?
How they will separate? So you have this main device, main amplifier that gives you the linear polarization.
Right.
That goes the same direction.
Right.
The outcome of delta. Are there any provision how you separate those?
Well, this daisy polarimeter can detect a circular.
I'm not asking how you measure.
Oh.
The question is how you separate, because this main device gives you a background that you have to get rid of.
It's not supposed to be a user device. It's really just R&D on future undulators like a delta, just to see if we can predict the polarization generated. Yeah, there'll be a big planar background. I think that's all there is to it. It's an opportunity to take one of 33 undulators, do a new scheme, and make sure we know how to do it for the future, which you like, I know. I'll wait for the next question. Yes, Alex.
How are you handling the microbunching instability in your bright beam?
I'm not sure. I heard microbunching instability and...
At LCLS-II?
Yeah, it's a big deal for us right now, Alex. You saw this very long 2.5 kilometer transport line that has space charge forces, even at 4 GeV, because of the short bunch. And we're studying it now with help from Berkeley, and we're finding, some beam damaging effects in microbunching, even with a laser heater, which you know well, turned on to its limited level. So we're having some trouble right now fighting that. And Marco Venturini at LBL has come up with a scheme. If you remember, there's lots of dog legs in this beam. We keep bending it over to avoid walls and existing structure. Every one of those bends causes a microbunching issue. And Marco Venturini has come up with a scheme to put small chicanes, dispersion-canceling chicanes near each dog leg, and he's testing it in simulation. And it looks like he can control the microbunching back down to a good level. But it's a problem right now because of this very long line where we do nothing but run the beam through.
It would impact the...
Yes, it would damage the energy spread effect, especially.
Energy spread effect in the...
Right. Sasha Zolens wants me to use it to drive the FEL with high spikes. He wants me to use this disadvantage, and he's probably right, but I haven't figured out how to do it yet.
Thank you.
Yes?
You showed one result on hard X-ray self-seeding, when you showed that the bandwidth narrows down quite a bit.
Yes.
And you also mentioned that there's a pulse-to-pulse variation.
Yes.
Is that just an intensity variation, or is it also wavelength variation?
It's not wavelength because the monochromator really locks that down. But imagine you have a very narrow bandwidth monochromator, and of course, as you jitter in energy as coming in, some part of the beam will hit that maybe. Maybe it gets so extreme no part hits it. So it's really just power fluctuation. But it's big. It's like 50%. And I'm quoting you a number from a year ago. There's a team put together that I'm not involved with that has worked on the LINAC energy stability, and they've got it down another factor of 2. So it's not as bad as that anymore. But it's still not as clean as you would like, not as stable as you would like. Any other? So thanks again to Argonne for inviting me.